Most people know about
read
how
stream
contrast was
is
done
pretty
today
cheap, so
in peer-to-peer, but we will just recap it a little. The old school was to download the whole file from one node, and then people quickly realized that's stupid, so they split it up and downloaded it from multiple sources. And then people started experimenting with file sharing swarms like BitTorrent. And I think most of you know how that works, but we'll go through it anyway because we use the same technique in several other areas. A BitTorrent swarm is actually a random network. So it's just a normal random network, and some of the nodes might be seeds, have 100% of the file. Some are, what do you call those that aren't seeds? Leeches. That's a fairly evil name, but okay.
Free riders.
Yeah. Sorry?
Free riders.
Free riders, yeah. But leeches are the ones that aren't uploaded at all. Those who both uploading and downloading are something else.
Seeders?
The seeders are those that have 100% of the file, but those that have 10% and are also uploading that 10%.
I think they're still seeders.
No,
Yeah, let's not see the peers.
Well, let's call them peers, anyway. Because I think leeches mean those who only download and help out and upload. So the new invention then was that someone has the entire file, for instance, just one node, gives it to his 3 neighbors, and those neighbors will have uploading to the other ones, and also they will exchange. So I can give one part of the file to him, one part of the other part, and then they will exchange their parts with each other, which makes it extremely efficient. So I think all of you know this principle, right? Yeah. One thing is that people forget, you can use this for real time, like sending a sports event in real time. Because this one, even if this one only have 2 megabit upload bandwidth, because that's one TV quality stream, you can send 1/3 in each direction, and then they will swap and forward it. So you can actually add any amount of nodes out here. You can have 1 billion viewers of your TV show. Also, as you might be superseding, have you heard that? But this one can upload on purpose different parts of the different nodes here, and then watch if you give part number 1 to this, and then wait and see if it actually reaches the other ones after a while. If it doesn't, cast that one off and stops feeding it, because that one obviously isn't sharing. So this one can be a bit smart and detect if they are misbehaving. You can't detect if nodes further away are misbehaving, but at least the closest ones. But that might help, especially when you start up a file sharing in the first hour. That can be very useful. So superseding should normally just be done when you start up. But later on, you can't really know, because many nodes will have each part, so you can't know if that one is actually sharing or the part comes from somewhere else. So it's just stupid to try to delay who gets which part. The blocks inside the file, we split them up in blocks. What do you call them, blocks? There's another name for it.
Chunks.
So,
Chunks.
chunks, yeah, chunks, okay. In some predefined size. We're going to talk more about the ideal sizes later on. So we give 1 chunk to each one, and actually we usually split the chunks up in smaller chunks, because we want to have smaller checksums in each part of that, but that checksum is just temporary during the transfer, so it's just like packet-based transfer. But when this one have gotten the whole chunk, we have a checksum on that one, and you can share it with other nodes. When we're doing it in not real time, like uploading a movie, then we try to, every node tries to spread their downloading out over all the packets. So if, for instance, the other chunks, if they notice that not many nodes have this chunk, it prefers to download that one, so it evens out. So even if a C disappears, there might be in total 3 instances available. At least 3 nodes have each of the chunks. You're aware of that thing too? Yeah, okay. But that meant people thought that you had to do like that. That meant they thought you couldn't do real-time transfers, like streaming transfers. But if you look at streaming transfers, if you think of, let's see, or not? Not really. Yeah, number of available chunks of each chunks, and here you have the different chunks. So you have actually the stream like that. If my node is watching that, if the user, the human, is watching the stream in that point, then of course I want the chunks in this area. So if I only downloaded those, I won't have these ones to share with other users. But other users might be looking at other parts. So what I do is I download some chunks over there, some chunks over there, but mainly in the area around where I'm looking, or actually in front of the area. So, something like that. So I focus my downloading here, close to where the viewer is, and spend a little time, like 25% or 30% of the time, downloading other packets. Because these packets, they don't help me out right now, but it gives me something to trade. As you know, BitTorrent does trading. So because if this node is uploaded to that one and that one isn't uploaded back, this node realizes he's evil, he's in sharing, I'll drop him. So you need something to trade with. And also these ones will anyway be useful for me sooner or later, because the user will probably anyway get there. And if the user started in the middle of the movie, like I often do, just to check if it's good, usually if he likes it, will anyway start over and start from the beginning. So this isn't especially wasteful anyway. And this means the number of available of each packet won't be as high, since we will be more of the part where people are actually watching. But still, you should anyway have at least one seed. And then as long as you have at least one seed, this works well. Because only if the only seed disappears, then you might be screwed in this case, but then you're usually screwed anyway. So this is good enough. It actually works much better than people think.
Are there systems that use this today? Or is this just
There are some systems. I don't know the names of them, but people tell me that such systems have been built and have been deployed. Yeah. So it's actually, you can still use the BitTorrent protocol. You just want to make the client slightly more intelligent to know which part you want to download first. So it's up to some intelligence in the client, but no change in the protocol whatsoever. But this only works, of course, if the stream has a defined start and end. If you don't have that, then you need to use normal BitTorrent, because BitTorrent can only address packets, predefined packets. But you can use the same thing if you have a real-time stream, because you can, for instance, number them by time or some other way. And then, of course, it wouldn't be like a shorthand, it would be more like less and less and less like that, perhaps, or something like that.
Yeah.
Because that will be infinite in both ends. But it's the same principle. So, not much more to say about that. Just that it works better than you might think. Yeah. So that's how to do TV and radio streaming, basically. Yeah, okay. There's an old myth in streaming of video and radio on the internet. At least 10 years ago, everyone thought that the solution was to use UDP for that, because some packets will disappear along the way. And if you lose packets, it will stop and buffer, as you have seen many times. So they instead used encoding. That meant in one packet they put the main data, but the same data but harder compressed were in some other packets further back. Then if you lost one packet, you could get the same sound and video, but with a lesser quality. So it didn't stop the buffer, your quality just went down. Are you guys aware of that system? No? So it's like 80% of the packet is the normal video and sound, and 20% of the packet is actually that data, but with much harder compression. So that is much lesser quality. So this packet is lost. Sorry, it should be other way around. It should be sent ahead. So this smaller amount is a harder compressed version of this big packet. So if this one gets dropped, I already have the harder compressed version, and can show that packet anyway, but in lesser quality. So that we used to do in UDP in the 90s and early 2000s, and it seemed to work well at first. It was a very theoretical model. The problem was, for most people, like, at least me, I rather have buffering, wait a few seconds and get full quality, then get really shitty video and really shitty sound.
Yeah.
Often so shitty that I couldn't hear what they were saying. So I rather wait a few seconds. So it's usually better to just resend. And another thing, if you use, most people when they, you know that TCP, you know that TCP is cooperating with all other computers in the world. Because if somewhere on the network, well, let's say this is the internet, if there is congestion here in this router, all the nodes that are sending TCP will notice that there is congestion because their packets will be delayed or dropped. So they will lower their TCP speed automatically. All TCP IP stacks in the world does this. So TCP is smart and handles congestion on the internet. UDP does not do that. So if you hammer away UDP packets, you will actually flood the internet. So when big video services on the internet started flooding the internet with UDP packets, the internet, well, more or less crashed. So I don't remember if it was around 2003 or something, then we were in trouble because there were several video services doing that. So what they should have done is made a smart protocol on top of UDP that behaves just like the TCP and goes down in speed and up in speed and does all that. But there's a hell of a lot of coding and a lot of science. Even like Microsoft couldn't handle this. They copied a Unix stack. They copied the code exactly because they had the same bugs in the stack. So my hacker friend said it must be a copy because exactly the same bugs. Because their older stack hadn't been doing this.
Trumpet Windsock.
Sorry?
Trumpet Windsock.
The good old
Yeah, but I don't know which one was this copy, but suddenly it was better, but it had the same bugs, so, but it was still better. So this is actually a hard thing to do properly. You probably read about it, most of you. Yeah, so implementing it yourself is hard. So the simple solution is don't do all this extra, just use TCP and accept buffering occasionally. That's, at least most users accept that. I don't know what you think about that, if you prefer shitty quality or buffering.
I suppose it depends on the use case, like, but in the video, like Netflix is basically grooving in, people will
Like, for instance, if I watch Swedish television, government television, or if it starts buffering too often, it changes to lower quality after like a minute and realizes you're a slow user and gives you a lower quality automatically. But with some delays, I will experience some buffering before that happens. But that means it doesn't waste 20% of the bandwidth of something I don't need. And I just get buffering for 1 minute and then it has adapted. And it does that on top of TCP. So I recommend using TCP for streaming anyway. And it seems almost all services have switched to that now. So this was a very nice theoretical model, but in practice, no. You might still find it in the literature, in university classes and like that. They're still talking about it, probably. This one. Oh. How many here knows what a hash tree is in peer-to-peer stuff? Okay. How many know what a hash list is in the same location? Yeah. Most people have not heard about the hash list.
I don't know what a hash trick is either.
Okay, yeah, I'll explain that. I'll just say how many. Yeah.
Okay.
Thank you for saying it. Because it's, yeah.
sometimes called like a Merkle tree.
Yeah, Merkle trees also, but most people don't know what it is. But I'll explain this. Actually, that's how these guys found me, because I wrote the article on Wikipedia about
That's why you're here. I read the article
Yeah.
on Wikipedia.
and Shakespeare wrote it. And
Yeah.
And then he found my stuff. So, yeah. But it's not my invention, not at all. For those of you who know, Pt1 uses a hash list. Many other modern peer-to-peer networks use a hash tree, but I'll explain it. If we have our blocks, we make